In today's lesson, we're going to learn about electromagnetic waves and their properties. Ankur here is going to take you through the theory part, and then we'll be solving a set of problems.
Okay, so basically we're dealing with electromagnetic waves here, and this is a pretty easy chapter, and you have a few concepts in this, and you have some formulae which you'll use to solve problems. So first let us start with electromagnetic waves and few of their properties. So here first we see the velocity of the electromagnetic waves in free space. So velocity of electromagnetic waves is generally denoted by C. So C is E naught divided by B naught. As you all know that electromagnetic waves are generated due to mutually perpendicular electric and magnetic fields. So E naught is the magnitude of the electric field, that is the amplitude, and B naught is the amplitude of the magnetic field.
Right.
Next it is also equal to 1 by root over mu naught epsilon naught. Here mu naught equals to this value, epsilon naught equals to this value. They are the absolute permeability and absolute permittivity of free space.
Right.
So after calculating by putting mu naught and epsilon naught in this equation, we find that C is nearly equal to 3 into 10 to the power 8 meters per second, which
Right.
is the speed of light.
Correct.
So this is a constant value, and you're expected to remember this because they might not provide this value in many questions, but they assume that you know this value, so you are supposed to remember it. So next we move on to conduction current. So conduction current is the current in the electric circuit which arises due to flow of electrons in a conducting wire of the circuit in a definite closed path. It takes place in a closed path.
Right.
So direction of current is opposite to the direction of flowing electrons. So it takes place in a definite circuit in a closed path in this same direction.
Right.
And if it's an alternating current, then obviously the direction would change, but we are not dealing with that. So next we go to displacement current. For displacement current, we have been given this formula ID, which is the displacement current, equals to epsilon naught d phi by dt. So here phi is the flux and d phi by dt is the rate of change of electric flux.
Right.
E here stands for electric, so it is the rate of change of electric flux, and epsilon naught, as I already told before, it is the absolute permittivity of free space.
Right.
So next we move on to Maxwell's equations. I'm just doing a revision here because you have already gone through this part in your electrostatics, current electricity, magnetics, and electromagnetic induction.
Correct.
So it's just a basic revision for you, and I'm not going into too much detail in this topic. So first we have Gauss Law for electrostatics. This law gives the total electric flux in terms of the charge enclosed by the closed surface. So if we consider this to be a Gaussian surface and there's a charge Q inside, so this law would give the flux associated with this surface. So it is the closed integral of E dot ds. Here consider E and ds as vectors. They are written in black. Consider them to be vectors. Equals to Q by epsilon naught. Q is the charge inside this closed surface.
Right.
So ds would be the area. Let's consider an infinitesimal area on the surface, and Q is the charge enclosed inside, and epsilon naught again is the absolute permittivity.
Right.
Next we move on to Gauss Law for magnetism. So this law shows that the number of magnetic lines of force entering a closed surface is equal to the number of lines leaving that closed surface. That is, if this is a closed surface and there are a specific number of magnetic lines entering, the same amount of lines would leave. So if 3 magnetic lines, let us say 3, are entering, 3 would leave. So it is basically a simple law which you have learned in your magnetics chapter as well. So B dot ds equals to 0 because the number entering is equal to the number leaving. So total, like if you take the closed integral, it turns out to be 0. So next we have Faraday's law of electromagnetic induction. This you have done in great detail in electromagnetic induction chapter. So
Right.
I'm just doing a basic revision here. So this law gives relation between electric field and changing magnetic field. You know that changing magnetic fields cause electric field and changing electric fields generate magnetic fields. So there's a basic relation between electricity and magnetism.
Which is actually the basic of
Yeah, it is the basic of electromagnetic induction, the basic concept. So again we have a mathematical statement, E dot dl equals to minus d phi b by dt. So it is the rate of change of magnetic flux. B stands for the magnetic field. So it is the negative of that. And again E and dl are vectors. You are supposed to consider black here as vectors.
Right.
So next we move on to Ampere Maxwell's law. This law states that magnetic field can be produced by conduction current as well as by displacement current. So again, this is again another law in electromagnetic induction. Here the magnetic field can be produced by conduction current and displacement current. That is basically electricity produces magnetic field.
Right.
So again we have E dot dl integration equals to mu naught IC plus E naught d phi E by dt. So here this term is the displacement current and this is the conduction current.
Right.
So again mu naught is the permeability of free space. So this is a constant. So this mathematical statement justifies, like gives off Ampere Maxwell's law in a mathematical way.
Right.
So next we have the speed of electromagnetic waves in any medium. The first topic that we saw was the speed of electromagnetic waves, that was in vacuum. But now we move on to any medium. In the speed of electromagnetic waves in any medium is given by V equals to 1 by root over mu E. Here mu and epsilon here are the permittivity and permeability of the material. So it is mu naught mu R is the total mu and epsilon naught epsilon R is the total epsilon. So here mu naught and epsilon naught are the usual absolute permittivity permeability, but mu R and epsilon R are the relative ones. So this in total gives this part. So it is C, this part gives rise to C and this part gives rise to N, where N is the refractive index. It is equal to root over mu R epsilon R, which is the refractive index of the medium. So with this we'll move on to the next topic. So here we have the next topic, that is the characteristics of electromagnetic waves. So electromagnetic waves are transverse in nature. So you need to know that the vibrations of the electric field and the magnetic field are perpendicular to the direction of propagation of the wave. So it is transverse in nature and the speed is same as the speed of light, 3 into 10 to the power 8 meter per second in vacuum.
Correct.
So the next property is the two fields E and B, that is the electric field and the magnetic field, have the same frequency. They have the same frequency of oscillation and they are in phase with each other.
Right.
That is the frequency of the resulting electromagnetic wave. So here we have EY equals E naught sine kx minus omega t, BZ equals to B naught sine kx minus omega t. These are the two wave equations of the electric field and the magnetic field respectively. So if a wave is traveling in the x direction, suppose a wave is traveling in x direction, the electric field would be directed in the y direction and the magnetic field in the z direction.
Right.
They all are mutually perpendicular to each other. So for this you should remember that if the electromagnetic wave is in the x direction, the electric field will be in the y and the magnetic field in the z. So if this is changed to some y or z, you need to do the corresponding changes to rotate the coordinate system and you should find the direction of the electric field and the magnetic field. Here E naught and B naught are the amplitudes of the electric and magnetic fields respectively. Here kx and omega t are the terms relating to the wavelength and the frequency, as you all know from like wave optics and wave and oscillation chapter. So next we go to the rate of flow of energy. Rate of flow of energy crossing a unit area in electromagnetic wave is described by vector S. Here it is also known as the Poynting vector. So it is defined by this expression: E cross B, E and B are vectors and this is the vector multiplication, divide by mu naught. Mu naught again, as you all know, is a constant. So the fourth thing we'll be discussing is the energy density of electromagnetic waves. here we have a lot of subparts. So remember all the formulas of all the subparts separately, because these are going to be used in solving problems.
Right.
So the first is the average energy density of electric field. So UE, E stands for the electric field. It is epsilon naught E square divided by 2, which is also epsilon naught E naught square divided by 4. So it is this formula that will mostly come into use, but you are supposed to remember this as well, because sometimes this might come into play. So here E naught is the amplitude of the electric field, as you should remember from the previous discussion. Similarly, we have the magnetic field as well. It is B square by twice mu naught, and the B naught square by 4 mu naught. So basically when you square this, just this becomes 4, as here also it becomes 4. Only difference in these two is that here epsilon naught is in the numerator, but mu naught in the case of magnetic field is in the denominator. Otherwise these two equations are basically just analytic to each other. They are just the magnetic analogy of the electric field, and similarly the vice versa. So we have another relation here, UE equals to UB. So the average energy density of the electric field and the magnetic field are the same. This is a very important relation, and you are supposed to remember this by heart. It should be in your fingertips, because this is one concept that might be used in a lot of questions in your competitive exams and board exams and anywhere you study electromagnetic waves. So you're supposed to remember this and make use of this property.
Right.
The next thing we are going to discuss is the total average energy density. So what do you think total energy would be? It is the sum of the electric field and the magnetic field average energy densities, because the energies of the electromagnetic waves is transported in the form of electric field and magnetic field. So obviously the average energy density would be the sum of both these.
Right.
So it is epsilon naught E naught square by 2. You know how this came, because it was epsilon naught E naught square by 4, and this, because of this relation UE equals to UB, this also became equal to this. So just multiply this by 2. It is epsilon naught E naught square by 2, which is also equal to B naught square by twice mu naught, which is double of this.
So the total average energy density is basically the double of the individual
either
energy
of the electric field or the magnetic field average energy density. Because of this relation, both are equal, so you can multiply any one either by 2.
Right.
So basically sum of these two would be twice of any one of them.
Right.
Next we have another property, very important property, that is intensity. So it is the energy crossing per unit area. One thing is unit area, the other thing is per unit time. So it is per unit area per unit time, and this must be taken into consideration. It is perpendicular to the direction of propagation of EM wave.
Right.
So if this is a surface, if this is an electromagnetic wave coming, so it will be, the intensity is measured when it crosses this surface, because it is this area and it is perpendicular to the direction of propagation of the EM wave.
Right.
EM wave, electromagnetic wave. So intensity is given by I equals to epsilon naught E naught square by 2 or B naught C by twice mu naught. So here just multiply C with this average energy density, and you are going to get the intensity. Next we have the radiation pressure. Radiation pressure is because of this phenomenon. When there is a surface and an electromagnetic wave comes and collides with it, it either gets absorbed or reflected back. So if this is reflected back, the pressure is twice I by C. I is the intensity, and if it is absorbed, then the pressure is I by C. This is because when it is reflected back, there is twice the change of momentum. Suppose it comes, it goes back, so there is twice the change of momentum. But if it is absorbed, the entire momentum is just transported to this system, so it is only once the change in momentum. So it is I by C here, it is twice I by C here. Totally reflected gives double the pressure of totally absorbed. So this is one relation that you should keep in mind, because there might be questions where there will be some part of a wave that is absorbed and some part is reflected, or it is either totally reflected, totally absorbed. So you should use the correct relation for that.
Right.
So for that fact, you should remember both of these and know which to use when. Next we have the electromagnetic spectrum. So this is the total spectrum of all the electromagnetic waves that we are familiar with. So for the lower frequency and higher wavelength, we have the long radio waves.
Right.
And then we have the radio waves, normal FM and AM waves in a slightly higher frequency. Then we have the microwaves, which are even of more higher frequency. Then this is the IR or infrared. Then there is this visible range where we have from 400 nanometers to 700 nanometers in wavelength,
Right.
starting from red going till violet.
All the light we can see.
Yeah, all the light that is actually visible to our eyes, the Vibgyor spectrum that we say. Then we have the ultraviolet, which are of even higher frequency. Then X-rays that have numerous applications in different like spectroscopy, as well as for human health related issues.
Right.
So for that we have X-rays. And finally the gamma rays, which are generated by the nuclei of certain atoms, and they are of tremendously high frequency and very less wavelength. So this is the entire spectrum, and we have different applications for different waves that we have here, and you are supposed to remember a few applications of the familiar waves like the radio waves, microwaves, infrared, UV, X-rays, etc. So those might be some conceptual questions, but you'll find their uses, applications in various books easily, and you're supposed to study it from there. And this is like a normal question in some competitive exams, where you have a direct question on the application of which wave is being used for this application.
Right.
So for that you need to know about the electromagnetic spectrum.
Right. So guys, this was the theory of electromagnetism. Now we're going to be dealing with a set of problems. So we'll start with the first question now.